Now, it seems like a lot to get from 3 lessons in one day, although each one lesson does not have very much. So that's not as crazy as it sounds. What I hope to do at the end of today is have some time for any homework questions. And that's something I'll try to do in general, just with each class period, is allow some time for that. So be sure to bring in questions. Now, you don't have homework due for a while. Well, I guess first time is due a week from today. Some of you have been reaching out to me with questions, so that's good. Anyone having difficulty, please think to do that, and I can try to get things cleared up. And if it seems to be something of like someone get a question from one student, but it might be of interest to the whole class, then that's something I would pass on, like in a Canvas message. So be sure to check your Canvas messages for anything like that. Okay, now, so our focus for the first portion of the semester is going to be on the heat equation. But a lot of what we learned about how to solve a heat equation can be applied to other PDEs as well. So the heat equation is a relatively simple one to start with. Also in the interest of keeping things simple for the first PDE you're dealing with in a concrete way, we're going to make it a problem that only has one space dimension. So we have this, what appears to be a terribly contrived situation of a rod, and we're modeling the flow of heat energy through the rod. And these conditions here are meant to make it a truly one-dimensional problem, just so we can focus on what's happening as a function of x and also a function of time. So that's why we're assuming that this rod has lateral sides insulated so that there is no heat energy flowing out the sides of the rod. It's only flowing from left end to right end or in the opposite direction. We have an initial temperature profile. So the temperature at any point of a rod from x equals 0 to x equals capital L is given by some function t0 of x. So that's an initial condition. We also assume that the left and right boundaries of a rod are kept at some fixed temperature. So this is one example of what's called a boundary condition. I'll have a lot more to say about boundary conditions later today, and there are different kinds of boundary conditions corresponding to different physical situations. So this is just one of them, fixed temperatures at either end. So these are constants. Well, actually, it could depend on time, but this is the temperature at x equals 0. This is the temperature at the other end, x equals L. Right. So the PDE and these conditions can then be solved, and we'll actually learn how to solve that on Wednesday to determine what the temperature will be throughout the rod over time. So from its initial temperature profile that has the temperature now, we'll see the PDE will give us the rest. So the idea is to take these conditions and translate them into equations that we could use in solving the problem. So what we actually have is an IBVP, and that is an initial boundary value problem. Okay. So in this section, I'll state the whole problem. So first ingredient in an initial boundary value problem is the PDE. So this is our PDE. This is a heat equation. Here I put in a coefficient, alpha squared.
I don't think we can see this.
Oh, something's okay. This is okay. Yeah, I'm scrolling. I did get an alert that said it was having trouble connecting to the network. So there appears to be an internet problem. Okay. I'm going to try. Thanks for letting me know about that. That's a bit of a problem. Okay. Oh, wait. Is it delayed or something?
It's delayed. It scrolled really late when you did it. Yeah.
I'll say. How am I supposed to work with that? Okay. What I'll try is if I stop sharing. Okay. So now I gotta wait for it to. That's pretty sad. Yeah, because now that I'm not sharing, that should just disappear from the screen, like it has on my screen. All right. Okay. All right, what I'm going to try doing is I'll try leaving a meeting. And yet still nothing has changed in the screen. That's really fantastic. Sorry, there's no holding back my snark at a time like this. That ship has sailed. Okay. All right, so now what I'll try is rejoining the meeting. Oh, okay. Finally, it was responsive. Oh, that's. I could not have that. Why is it doing that? Oh, it still shows my video system. Okay. Okay. Still says we're having problems connecting to the network. All right. I'm trying to share my screen again. Let's see how long it takes to come up. Come on. All right. Sorry about that. But I guess I'm apologizing on behalf of iTech. It seems to be scrolling. Okay, so so here's our PDE. UT is alpha squared UXX. Alpha is a constant, is a coefficient that indicates thermal conductivity. And we also indicate the domain of a problem. So here we have spatial domain, x between 0 and L, and then the time domain starting from 0 to infinity. What's bugging me here is I'm moving my mouse, point out various things, and the mouse is not moving with me, or at least not in a timely manner. Yay. Now, if I use here, you may recognize this. This is similar to the definition of derivative. So remember, like f of x plus h minus f of x over h. We're not taking a limit here, but this is only an approximation of the derivative at the point xt. And here is also resembling the definition of derivative. If I take this expression and replace delta x with minus delta x throughout, I get this. This is called a forward difference. This is called a backward difference. And if I take the difference of these two to approximate the second derivative, then this is what I get. So this minus this over delta x gives me a center difference for a second derivative. Now, if I substitute this approximation in for uxx here, then this is what my PDE looks like. Here I have the average of u at neighboring points. So x plus a little bit, x minus a little bit. And then here I have minus u of xt. So what we have here is the difference between u of xt and the average of its values at neighboring points. Now, if u of xt is greater than this average, that happens when the function is concave down, which means that uxx is negative. Whereas if the average is greater, that's when u is concave up, so uxx is positive. So suppose that in this case, this average is greater, so concave up, this whole expression is positive. That means that the temperature is going to increase. If u is concave down, the temperature is going to decrease. So the concavity of u indicates the direction of a temperature, increase or decrease. So this is one way of looking at, of interpreting the heat equation. All right. But this is just one ingredient of the initial boundary value problem. Because I can show you, and I will show you on Wednesday, how we actually get a solution to this. But the solution will not be unique. In order to ensure that we have a unique solution, we need more information. Let's see if scrolling works. Okay, scrolling is working. So here are the other pieces that we need. Boundary conditions and initial conditions. So in this case, in the example I've given, the temperature is fixed at the left and right endpoints of a rod. So at least these boundary conditions, u of 0t is T1, u of LT is T2, and it's equal to these temperatures for all time. Here in this example, these are constants, but they don't have to be constants, they could be functions of time. And finally, initial condition, that when t equals 0, the temperature is equal to this value T naught. So between the PDE, the boundary conditions, and the initial conditions, we have a problem that has a unique solution. Are there any questions up to this point?
With that initial condition, that's at time 0, right?
Yes.
Okay. I got a bit confused with the bullet point about it, because it said it's warmed or cooled to a fixed temp T. So, but it starts at
Oh, wait, are you referring to?
fixed temperature T.
Oh, okay. All that means is whatever, like whatever temperature rod happens to be, which could be anything at first, we make sure that it has that temperature. At that T equals 0.
Okay.
Yeah. And if it's something that I take it from a textbook, there's probably no need to go into that. But the point is, this is what we assume. Yeah, so this here is meant to like set up a problem so that the behavior of a temperature will conform to this initial boundary value problem. Other questions? Check the chat. Okay, now here are some variations on a heat equation. So different PDEs for modeling different situations. So in the problem that I stated earlier, the rod was insulated so that there was no flow out, no heat flow out the sides. This makes it a truly one-dimensional problem. Oh, dang it. Yeah, I saw it again on my screen that I'm having trouble connecting to the network. Oh God, what? I don't know if it's something that will recover in a little bit.
Yeah, I thought it was gonna just load in, so that's fine.
Why? I still have time for this. All right. Well, this was going well for a while. Okay. I'm trying to stop sharing and reshare. And sometimes when I tell it to share, it's just like, no, I'm not going to. You have to wait until it feels like it. Okay. So, so the previous example, the rod is insulated, so there's no heat flow out the sides. Here, this PDE allows for heat flow out the sides, lateral heat loss, and we assume it's proportional to the temperature difference. Compared to some specified temperature U naught. So if, suppose U is greater than U naught, then this whole term will be negative, meaning the temperature is going to decrease. Whereas if U is less than U naught, this part is negative, the whole term is positive, so the temperature will increase based on that. Now there's still this to take into account, but that's how this term would affect the temperature. A previous equation assumed that there were no external heat sources, but suppose we do have that. So we'd have some term f of xt that indicates temperature being added, or it's a heat source, or it could be a heat sink, so causing a temperature decrease. And then here we have not just diffusion. This part, the main part of the heat equation, causes diffusion, models diffusion. We could have another term that models convection. So we have this term involving just the first derivative of u with respect to x. So here's a real life example of what could lead to a term like this in the PDE. Because if these particles convected upward, and then this term leads to diffusion of those particles. So when you see a second derivative term, an equation like this, that's diffusion. First derivative term is convection. And now and then we'll deal with PDEs like this that have these additional terms and figure them out.
You said one derivative is convection?
Yes. Then you can also have a term that's just u, not a derivative at all, just u of xt times some coefficient. That's a reaction term. So, the diffusion, convection, reaction are the kind of effects we can have. Now, so I've shown you a few different kinds of PDEs related to the heat equation. Here are some different kinds of boundary conditions. The first kind is one from the original example, where you have fixed temperatures specified at the left boundary and the right boundary. So the most general kind of boundary condition of this type, type 1, that's called a Dirichlet boundary condition. So when the value of the solution is specified on the boundary of your domain, that's called a Dirichlet boundary condition. So here they can be functions of time. So this is the easiest boundary condition to work with. Actually, I know it's kind of weird. Type 1, type 2, type 3 is how we're identified in the textbook, but it actually makes more sense to talk about type 3 first. Also a relatively simple condition. The first derivative is specified on the boundary. So du dx at x equals 0, x equals L, is set equal to something. That's called a Neumann boundary condition. So Dirichlet boundary condition specifies u, Neumann boundary condition specifies du dx. So in the case where the rod is insulated at the end points, we would say that du dx is equal to 0. Now, it may be equal to some non-zero value for some other physical situation, but insulation means the temperature is not allowed to change. So it may not be, it's not that some specified fixed value like before, it just has to remain stationary. Now here we're dealing with PDE in only one space dimension. If this was in higher dimensions, instead of specify, we would use the normal derivative. So a normal derivative is the gradient dot product with the normal vector to the domain. Oh, more network trouble. Let's see what that does to the screen. Sure enough, I'm scrolling and you can't see it. Okay. I guess I'll just have to keep doing this ritual. Okay. So apparently the magic trick is to unshare and reshare. Multiple times. Okay, at least it worked faster that time. Okay. And now we have what's called a mixed or Robin boundary condition. Mixed because it works with both the value of the solution at a boundary point and the first derivative at the boundary point. Both are involved. Okay. So the flux, which is the flow rate of heat energy per unit of area, is given by this expression at x equals 0 and this expression at x equals L. So this comes from Newton's law of cooling and specifies that this is what the outward flux is. So heat energy leaving the rod. Now, we take into account Fourier's law of cooling. So all the laws of cooling come together. Says that this outward flux is proportional to the inward normal derivative. So leads to these two boundary conditions, this one at x equals 0, this one at x equals L. Now, the inward normal derivative at the left boundary, that's du dx, because it's how u is changing as x increases. When you're at the left boundary point, when x is increasing, you're entering the domain, the rod. So here we have constant times du dx. Here, we have to include the minus sign because when you have du dx, that's rate change as you're going from left to right. And at the right boundary point, that means you're leaving the rod. but we require inward normal derivative, so that's minus du dx. So these are the kind of boundary conditions that we specify when the rod itself is not prescribed to be a certain temperature, but the rod sits within a medium of a prescribed temperature. So for instance, suppose one end of a rod is sitting in water that is heated or cooled to a specific temperature, this G1 of T at the left endpoint or G2 of T at the right endpoint. So when there's a temperature of a surrounding medium, this is a boundary condition we use. Whereas if the rod itself is pegged at a certain temperature, that's a type 1 or Dirichlet boundary condition. So it's important to understand the difference. So, I pose this question to you. What if one end of the rod is insulated and the other end of the rod is immersed in water that has a constant temperature? What boundary conditions are you supposed to use in this situation? So you are allowed to have boundary conditions of different types at different portions of the boundary. So let's assume here, I'll just make this more practical. The left end of the rod is insulated, while the right end is immersed in water at constant temperature. So what types of boundary conditions are called for at the boundaries in this case?
Left is Neumann.
Yes, the left is Neumann.
Right is Robin.
If the right is a Robin boundary condition. It's immersed in water at a constant temperature. Are there any questions about these types of boundary conditions?
So for the Robin, when it's talking about G, when it's talking about G1T and G2T, those are both, they're not the ends of the rod that it's
Right.
talking about, it's the conditions around the.
Yes, the temperature of the medium.
Okay.
Yeah, so for instance, if the right end of the rod is sitting in water at the temperature of 30 degrees Celsius, then G2 of T would equal 30. This actually relates to one of the questions that will show up in the first test, where you're given the problem conditions in words, and you're supposed to write down what the problem is, like in terms of what, specifying the IVVP. What is the initial condition? What are boundary conditions based on the verbal information given? Other questions?
H is a coefficient, right, not a function.
Yes, it's a coefficient. Yeah, heat exchange coefficient. And then, yeah, here we have another parameter K. It's also a constant factor.
So for that problem, we would have two separate answers for that?
Well, you have one boundary condition, different boundary conditions in each column. It's still one problem. So you have some condition on the left boundary, some condition on the right boundary. So as long as you have something at each boundary, the problem is well defined and will have a solution. I can take you through the derivation of the heat equation from physical principles. So we have a heat equation, and this time we have an external source, so called capital F of xt. There's something that will be known. We have some specified diffusion coefficient as well. The same spatial domain. So temperature in the rod. So we'll have these assumptions basically to justify this PDE. So because it's laterally insulated, that means we don't have to include a term for lateral heat loss. The rod being made of a homogeneous material, that's what justifies making this coefficient a constant. You can have a variable coefficient heat equation where this coefficient is a function of x, but because it's a homogeneous material, it's a constant in this case. In this class, we deal mainly with constant coefficient PDEs, for which we have solution methods that let you write down formulas of a solution. Variable coefficient PDEs, those kind of analytical techniques do not apply. So you have to rely on numerical techniques. So solve those. That's my research program. Okay. Also, again, to make it a one-dimensional problem, we assume that the rod is so thin that there's not much temperature variation within a particular cross-section. Right. So now that we have the right assumptions to justify this PDE, here's our actual starting point for deriving it. This principle of conservation of energy. So the amount of heat within an arbitrary segment of a rod. So we have a rod that starts at some point x and then goes as far as x plus delta x. So the net change in heat energy within this segment of the rod is based on conservation of energy is matched by these two effects. So we have inward flux across the boundaries of the segment. So what's causing change in heat energy within the segment? Well, heat energy entering the segment. So that's what this first term is for. And then, if there's any heat generated inside a segment, for instance, by an external source, then you have to account for that too. So whatever causes the amount of heat to change in any way is what you have on the right side. Now you could have heat entering or leaving. You could have a heat source or a heat sink inside. So, you could have effects that add or subtract from the amount of heat in this segment. But whatever you have, you add it up, and it must be equal to this. So what we need to do is take this mainly verbal principle, conservation of energy, and write it as an equation to get to a PDE. So how do we describe the amount of heat in some segment of a rod as this integral? So here we have specific heat, which is a term that I don't think I've ever heard since my 8th grade science class. The density of a rod, and then cross-section area, and then we have a temperature. So taking all of these and integrating from or segment AB gives you the amount of heat in AB, and this is in calories. So what you see here is going to help us get to the left side. Now, So here we have the actual left side by taking its derivative with respect to time. Because this is the amount of heat, we actually want the change in heat over time. And C, rho, and A are all constants, so we pull them out of the integral. We're taking derivative with respect to t, so that just means we only have to put a du dt here. Because we're taking the integral with respect to the spatial variable. Now, I'm not using x here because I can't do that down here. X is one of my limits of integration, so I'm not allowed to use x as the variable of integration. These two have to be different. When it's a definite integral, so that's why I've changed to s here. But s still refers to the spatial variable. Really, I'm taking a time derivative of this whole expression. But again, because I'm integrating with respect to a spatial variable and these are constants, I can move that differentiation in respect to time inside the integral and just apply it to this. So that's the left side of my conservation of energy relation. For the right side, this accounts for heat energy entering or leaving garage. So it's entering through the left side or the right side. Now, one thing I wanted to point out is if we go back to the type 2 boundary condition, here we have outward flux. So outward flux is KUX on the left side minus KUX on the right side. But in the conservation of energy relation down below, I want not outward flux, but inward flux. That means these terms that represent outward flux, I have to negate them. So if I go back, right here, this is the term corresponding to flux at the left end of this segment. So because I want inward flux, I'm negating it. Here I have the term for flux at the right end, and it's not negated to make it inward. That's why it's opposite sign says almost up above. So K times UX, that's flux, so flow rate per unit area, then we multiply by the area to get the total flux coming into the boundaries of this segment. And then the other term, total heat generated inside the segment. That's where we count for the external source. We take the integral of that over the segment, and we're also multiplying by a cross-sectional area. So now, this is the translation into an equation of our conservation of energy. And notice how F is the amount of heat generated per unit of length, per unit of time. So it's important to make sure that you have the units correct on that. And so questions about how we arrive at this? Now, still a bit of work to do to get from here to a PDE. And the way we do that is use a fundamental theorem of calculus that anytime you have a difference of function values, which is what we have here, the difference of ux at two different x values, x plus delta x and x, that can be written as an integral. Oh, there should be a capital P. So here, GB minus dv is equal to the integral of this derivative. So if we apply that to the flux term, it's the integral over the segment of the derivative of KAUX. But K and A are constants. So we take the derivative of UX with respect to X. So that's where the UXX appears. believe that the scrolling is still working. Whoa, okay. So now, the entire right side can be expressed as an integral over the segment. And we had a factor of a in all the terms, so just cancel it out. Now, I write all of this as an integral on the left side, then equal to 0. So everything got moved to the left side. I also divided by c times rho, the specific e times the density. And so then I define alpha squared from this constant k that appears in the flux over c rho, and then I define capital F from little f, also from dividing by c times rho. It's just notational convenience, nothing more. Just to make the equation less cluttered. But now we have the integral over the segment of this has to be 0. But this is an arbitrary segment of a rod. The only way to have an integral of a function over an arbitrary subdomain equal to 0, regardless of what subdomain it is that this function must be equal to 0 throughout the entire domain. So in other words, we can just say that this integrand, this has to be 0 throughout the rod, and out pops the heat equation. So that's how PDEs are derived. I'm just showing you this one example, but it holds a number of cases too, where you have some kind of principle like conservation of energy, and that tends to deal with some kind of portion of the domain of your problem. So then you express that conservation relation as an integral over an arbitrary subdomain. Then you rearrange it so that that integral is set equal to 0. Because it's an arbitrary subdomain, the integrand must be 0, and your PDE falls out. So questions about what happened here with derivation?
Why is alpha squared used?
Oh, as opposed to just plain old alpha?
Yeah.
It's to, again, it's a notational convenience, but it's to affirm it as positive.
Okay.
It's not so, it's more helpful with the, actually the wave equation, because whatever coefficient you have, you often, in describing a solution, you often work with the square root. So it's a notational convenience in that case. But yeah, it's not something that's absolutely necessary. Other questions? In spite of the technical difficulties, I have reached the end of the notes, and we have time, which is good, because now I can take homework questions. I'm share so I can put a pulse book too. Okay. So it, all right. So are there any questions? Yes.
Can we look at number 5?
Okay, number 5. Alright. There's a question about that or this one?
Like, do you just get the, you integrate both sides first, right?
Yeah, so for this one, you'll first integrate with respect to one of the variables, let's say x. In that case, that part is much like this.
Yeah, that's what I got.
And then integrate the result with respect to y to bring it back to u on the left side, and then we'll get the right side.
So when you integrate with respect to x, do you just remove the partial derivative of x from the bottom?
Yeah, and then the 2 also.
Okay.
Okay, so you can do integrations to reverse a partial derivative.
Yes, you can.
So when you integrate the right side, like so for instance on number 5, when you integrate the right side in respect to x, are you assuming that constant is just some arbitrary function of y?
Yeah, if you're integrating with respect to x, then yes, you would get an arbitrary function of y, because then you take a derivative of that with respect to x, and you get 0.
Okay. So it would be wrong just to write c instead of actually writing out the function, like for instance, function of y.
Yeah, you would not have a most general solution in that case.
Okay.
So yeah, you would be getting a solution, but it might not satisfy whatever other conditions you might have.
Okay.
By contrast, for this one, when you integrate both sides, you would get a constant when you integrate 0, because this is a function of one variable as opposed to a function of 2.
Okay, I see. Yeah.
So when you integrate the right side again, we just get like any function?
Yeah, because what happens is, if you have some arbitrary function, and then you integrate with respect to its variable, like, okay, let's suppose you had f of y. Now, if you're integrating that with respect to x, you multiply by x. But if you're integrating with respect to y, then you're going to get its antiderivative. So it's perfectly fine to simply define what you're talking about.
So would the answer just be like infinite? Right?
I'm trying to give away answers in class, but I am comfortable saying that any of these problems that I mentioned here have infinitely many solutions.
And when you do, so you take the partial derivative with respect to x, and then you have an arbitrary function of y. When you take the not derivative, integral again, do you have an arbitrary function of x or?
Okay, wait. So let me just. All right. So you're saying that you have an arbitrary function of y,
Right.
and then you integrate with respect to.
With respect to y.
Yeah. So then, think of an example. Like suppose that function of y happened to be, let's say, cosine of y. When you integrate with respect to y, you get sine y.
Right.
So you're getting its antiderivative.
Okay.
Whatever that may be.
So you don't get any sort of like arbitrary function of x, even though you're still integrating a function.
Well, I guess you can think of it as a function that is the integral of an arbitrary function, which in a sense makes it arbitrary, but you know something about it.
But it's still of y and not
Yes,
of x.
exactly. That's the main thing. Yeah. But then you have to think about, okay, how do you handle, what do you do with that integral, or with the second integral with respect, like you've already integrated with respect to x, now you're going to integrate with respect to y. What are you adding on to it? And that's, because when you're taking an indefinite integral, you have to add on something.
Right.
And what do you add on in both cases? So that's right. So pay attention to that to make sure that you have the most general solution.
And that last add-on is the antiderivative of y.
Well,
Of that arbitrary.
you're going to get the antiderivative, but you have to add something onto that.
Is that where the arbitrary function of x comes in? Okay.
Yeah.
All right.
Yeah,
That's
Yes.
that's what I'm.
And it's a good idea when you're solving PDEs like this. It'll get more cumbersome in the future, but certainly with these. Go ahead and plug your solution back in. Make sure it works. Yes.
As for part two, is it asking for the second derivative of y and the derivative of x squared, or also the second derivative of x?
Well, okay, but this right here?
Yeah, that part.
This is just y double prime.
Oh, right.
Yeah, so you're again integrating twice, it just plays out a bit differently. So although you still have infinitely many solutions, this one's going to be a little more concrete just because it's a function of only one variable. Other questions? Or do you want us to link it out here? Still have time. Well, a lot of time.
There were some parts of the notes that I missed. So one of them was a net change inside. It was from the section on the derivation of the heat equation.
You need to see this again?
Right.
Oh, this is,
Right.
and this will all be posted in Canvas.
And then where it says C row A, right?
Oh, this?
It down further is the next one. Yeah, I just need to write down the F of X T.
So the homework, do you turn it in like on Canvas, or do you just?
In Canvas.
Do you have like a preference to like PDF or like just an image or like
Let's see. PDF is easier.
Okay, that's all.
Okay. Any other? Or, well, that's for Wednesday. So